Hey guys and gals, getting on here to review the combined gas law with you. As I said in my lecture, it's very similar to the other gas laws that we discussed, only instead of just dealing with two variables, you're dealing with all three variables within the same expression, okay? So in every one of these, you're gonna have initial pressure, initial volume, final temperature, final pressure, final volume, initial temperature. And then you're going to rearrange to solve for whichever one you don't have, right? So encourage you to identify all your variables, arrange the formula as you need, and then plug in those the actual numbers from the problem. Okay, so let's take a look at this. I'm going to work number 2 with you. I've already had a few questions about that one, so let's take a look at it. And it says, a sample of argon has a volume of 5.0 decimeters cubed, and the pressure is 0.92 atm. If the final temperature is 30 degrees Celsius, the final volume is 5.7 liters, and the final pressure is 800 millimeters mercury, what is the initial temperature of the argon? So first of all, what we're looking for is our initial temperature, which is T2, which is what we're searching for. The very first value given in the problem is 5.0 decimeters cubed. So 5.0 decimeters cubed. That's an unusual unit of volume, but we can work with it. We'll come back to that in just a second. The pressure is 0.92 atmospheres, okay? And then it has a final temperature of 30 degrees Celsius. Add 273 to that, so you'll get 303 Kelvin for your final temperature. Final volume of 5.7 liters, okay? And let's see, final pressure is 800 millimeters mercury. Okay, so first of all, we have a few things we need to do. We have 2 different units of volume. We have 2 different units of pressure. This is an issue. We just can't leave it like this, okay? Camera's a little blurry. Okay, so what we need to do is we need to be looking at apples to apples for our pressures, apples to apples for our volume. We know the conversion factors for pressure, right? I know 1 atmosphere equals 760 millimeters mercury, right? So if I'm trying to get from millimeters of mercury to atmospheres, I simply multiply atmospheres by 760 to get to millimeters of mercury. So I'll multiply 0.92 by 760 in order to cancel atmospheres and to get millimeters of mercury. And you should get 699, and at 0.2, but I'm just going to round there, 699 millimeters Hg. Okay. So now our units of pressure are the same, so that's good. I'm going to erase this because I'm going to need all the space I can for working this problem in just a second. So now if we look at our volumes, they are not in the same units, but hey, that's okay, because guess what? 1 decimeter equals 1 liter. So they're identical values, just different units. So I can just put 5.0 liters here. You could also do the opposite. You could just put decimeters cubed, 5.7 decimeters cubed here instead of liters. I just prefer liters, so I'm just gonna make them both liters. Again, personal preference. All right, so we're looking for T1. So we're gonna do P1, V1, T2 divided by P2, V2. And then we're going to plug in our values. All right, T2, 303K. Running out of space here. I'm missing my big whiteboards at school, you guys. Okay, 800 Hg. And then V2, which is 5.7 liters. Okay, multiply across the top, divide by the bottom. Anything that repeats on top and on bottom cancels. So millimeters of mercury cancel, liters cancel, and you end up with Kelvin. The cancellation part is why we had to convert those in the beginning. Otherwise, especially our pressures would have caused an issue here, okay? So we're gonna be ending up rounding to 2 significant figures because our 5.7 or 5.0 both have 2 significant figures. I know what you're thinking. This 800 point does not just have one significant figure, but remember, when somebody puts a decimal after those placeholder zeros, that makes them significant. I'm gonna make that a little bit more obvious, that point there. That makes those zeros significant. So that would have 3 instead of 1. But we go to the smaller number of sig figs. 5.7 is 2, 5.0 is 2 as well. So we're gonna round to 2. So you're gonna end up with I'm sorry, I was looking at question 1. 232 Kelvin, which you're going to round to 2 sig figs, which would be 230 Kelvin. I've been trying to make sure that I'm showing rounding for sig figs here, because I notice a lot of you're ending up with 232 and you feel like you got the question totally wrong because I'm telling you the answer is 230. You just need to round for sig figs. And I haven't been taking off points on that on your work, you guys. If you put 232, I won't mark that wrong. However, especially those of you going on to AP or college chemistry, I'm reinforcing the sig figs for you because you're going to be held accountable for that. Okay, I'm going to pause the video for just a second and we're going to work on another one. All right, you guys, let's look at number 1 together. I know I'm going backwards here, but the first question that I had this week was about number 2, so I wanted to make sure we got to it. If you hear something crazy, the wind is nuts right now. So if you hear like whooshing, it's the wind outside. So let's look at number 1. There's a particular reason why I wanted to do this one, and we'll highlight that. A sample of sulfur dioxide occupies a volume of 652 milliliters at 40 degrees Celsius and 720 millimeters mercury. What volume will sulfur dioxide occupy at STP? So when you're identifying your variables, just start with the first number, okay? 652 milliliters. That is your V1. You don't actually have to convert this to liters unless you want to. You absolutely can, but we'll get to that in just a second. At 40 degrees Celsius. So we need, so our T1 is 40 degrees Celsius, which we add 273 to, so it's 313 Kelvin. Let's see, and 720 millimeters of mercury. Let's see, what volume will sulfur dioxide occupy at STP? So what volume, our question mark is our V2, will it occupy at STP? So let's break down what STP means. STP means standard temperature and pressure. You guys know that, right? So standard temperature we know is the same as our conversion factor for Celsius and Kelvin, 273. That's the T in STP, standard temperature. The pressure is a little bit more complicated. I've covered this in a couple of my videos, but I just wanted to touch base on that again. Standard pressure, there's 4 different values for it, and you can use whichever one you want or whichever one fits the problem best. So 1 atmosphere, 1 ATM, and you can put as many zeros behind that as you want. So you want to put 1.0, you want to put 1.00, however many sig figs you need in the problem, okay? So 1 atmosphere is standard pressure. So is 760 millimeters mercury, okay? So is 760 torr, and so is, I'm gonna do it on this side because I'm running out of space, 101.3 kPa. Each of these are standard pressure. They just are standard pressure using different units. The cool thing is there also are conversion factors between each unit of pressure. So let's say in a particular problem you have millimeters of mercury and you have atmospheres. Like on the last question, we used this ratio to convert from one unit of pressure to the other to make sure that they were the same. So in this particular question, these are all standard pressure. So one of these I'm going to use for my P2, but which one? Well, my P1 is in millimeters of mercury. So I'm going to choose the standard pressure that matches the one already in the problem. I'm going to choose 760 millimeters mercury to make my life easier so I don't have to convert anything. Does that make sense? Hope so. Okay, and standard temperature is 273 Kelvin. So standard temperature, standard pressure. Good? I hope so. It's really hard whenever I'm used to having you guys in class, and when I go good, everybody might go good back, or they might go, can you go over that again? So I'm really missing that feedback from you guys. Okay, so now we need to rearrange our formula to find V2. So we're going to do this guy over P2 T1. Plug them in. T2. That says 273 Kelvin, which you get here. I'm so sorry, I'm running out of space, you guys. All over P2. T1. Millimeters of mercury cancel, Kelvin cancel, multiply across the top, divide by the bottom. Your answer is going to come out in milliliters, okay? Because milliliters are the only thing that don't convert. As I said in the beginning, if you choose to convert volume to liters here, that's totally fine. Instead of putting 652 milliliters, you put 0.652 liters. And your answer would have the same number of significant figures, be the same. It will be smaller than our final answer here. So multiply across the top, divide by the bottom. Everything here is limited by your sig figs in the 720. So that's going to be 2 significant figures. You plug this in and it's going to come out to, I think it's going to come out to 539 milliliters, but I need to round that for sig figs. So we're going to say 540 milliliters. If you had converted to liters, it would be 0.54 liters. So either of these 2 answers here are acceptable. If you guys have any questions or problems, I'm looking over this worksheet, and it's a little bit more rigorous than the ones that we had done last week. A little bit more converting and that kind of thing. So if you are having any problems, please feel free to reach out via email, and I can do a second review video if need be, okay? The other things I want you to watch out for, in these problems, there's a little tiny bit of extra information. So in question 1, which we just completed here, it said a sample of sulfur dioxide occupies a volume of blah, blah, blah. The sulfur dioxide is not really important to this problem. So don't get distracted by that extra information. Just focus in on those numbers, rearrange your formula, identify your variables, plug them in. Okay, that's it. Have a great day, you guys. Looking forward to posting new stuff on Monday. Bye.